Hi everyone, welcome to This Explainer. Okay, so today we're taking a look at a really fascinating connection. We're going to link the sweat dripping down your face during a heavy workout directly to, well, the numbers printed on your monthly electricity bill. Sounds a bit crazy, right? But it's actually all about energy, how fast we use it, and exactly how we measure it. By the time we wrap this up, you're going to look at your toaster, your light bulbs, and honestly, even your own two legs in a totally different way. So let's just jump right in. So picture this. You're standing at the bottom of a flight of stairs. If you stroll up those stairs nice and slow, you'll probably barely even notice the effort. But if you sprint up that exact same flight, you are going to reach the top totally winded, muscles burning, body practically radiating heat. But here's the wild biological and physical paradox. Whether you're walking or running, your body is applying the exact same force against gravity, and you're covering the exact same vertical distance. In pure physics terms, you're doing the exact same amount of work, and your gravitational potential energy increases by the exact same amount, right? The work is identical. So why in the world does a sprint leave you so completely exhausted? Well, the secret ingredient here, the thing making you so tired, is simply time. See, when you walk, you're taking the chemical energy stored in your food and turning it into kinetic and thermal energy pretty slowly. It's a nice, slow energy transfer. But when you sprint, you're forcing your body to do that exact same chunk of work in a vastly shorter time window. Your muscles are furiously transforming chemical energy into motion at breakneck speed. So it's really not just about how much energy you use, it's about the rate at which you're using it. And that, my friends, brings us to the core physics concept we're unpacking today, which is power. In physics, the word power, usually just represented by a capital P, describes exactly this. It's the rate at which energy is transformed, or the rate at which work is done. Basically, it's just a measurement of the speed of energy transformation. That's really all it is. And calculating it, it's actually a super straightforward three-step process. First, you just figure out the change in energy, or the net work done. Second, you find the time interval it took to actually do that work. And finally, you just divide the energy by the time. Power equals energy divided by time. It's a beautifully simple, incredibly practical relationship that governs so much of what happens in the world around us. Now, since energy is measured in joules and time is measured in seconds, power is technically measured in joules per second. But we have a special, much catchier name for this in the standard metric system, the watt. It's named after James Watt, the Scottish engineer behind the first practical steam engine. So the big takeaway here is that 1 watt is literally just 1 joule of energy being transformed every single second. From now on, whenever you hear the word watt, I want your brain to immediately translate that to joules per second. Okay, let's put some numbers to the human body. Take a swimmer, for example. If she transforms 2.4 kilojoules of chemical energy into kinetic and thermal energy over, say, 12.5 seconds, run the math and she's producing about 190 watts of power. Now think back to our stairs. If a 64-kilogram student hustles 3.7 meters up to the second floor of their school in just 5.5 seconds, they are generating roughly 420 watts of power. So your body is essentially this biological engine, pumping out hundreds of joules of energy for every single second you're in motion. Kind of mind-blowing when you really think about it. But obviously, we aren't the only engines out there transforming energy. Think about a toaster getting your morning bagel nice and crispy, or a heavy electric bass guitar roaring through an amp at a concert. They look completely different, sure, but they're doing the exact same fundamental thing your leg muscles were doing on those stairs. The toaster is just transforming electrical energy into thermal and radiant energy. The guitar amp, it's transforming electrical energy into sound and thermal energy. And just like us, electrical devices can do this energy transformation slowly or really, really quickly. Which brings us to electrical power. Basically, when an appliance transforms energy faster, we call it more powerful. You know when you look at the back of a device or a light bulb and you see a number with a big W next to it? That's the power rating. It's literally telling you the maximum speed of energy transformation that specific device is capable of. And the sheer range of power we use in everyday life is absolutely staggering. Like a laptop computer, it requires a pretty modest 20 to 75 watts to run its processors and light up the screen. A refrigerator sits somewhere between 100 and 500 watts. But then, look at a kitchen stove. Getting multiple elements hot enough to boil water and cook food requires this massive, super rapid transfer of energy. We're talking a power rating anywhere from 6,000 to a whopping 10,000 watts. That is thousands of joules of electrical energy turning into heat every single second. And it scales up even more once we step outside the kitchen. Imagine an electric elevator motor that has to lift a heavy, packed car 12 meters straight up in just 16 seconds. That job requires about 18 kilowatts, meaning 18,000 watts of power. And to keep all these appliances and elevators running across a whole city, we rely on massive generating stations. The Pickering Nuclear Power Plant, for instance, has a power rating of 3,100 megawatts. That is over 3,100,000,000 watts of power continuously pumping into the grid. It's an unbelievable amount of energy. Which leads us nicely to that little device attached to the outside of your house, the electricity meter. The energy companies use these to meticulously track the total amount of electrical energy your home is transforming. And here's the kicker. They don't just care about how powerful your devices are, they care deeply about how long you actually leave them running. Because at the end of the day, that combination is what determines your bill. Now, to calculate that bill, your provider doesn't use the basic joule. Honestly, a joule is just way too small of a unit to measure a whole house's energy use. Instead, they use something called the kilowatt hour, or kWh. Since power is just energy over time, total energy is simply power multiplied by time. So if you take the power in kilowatts and multiply it by the time the device is left on in hours, you get your energy consumption in kilowatt hours. That is the actual energy metric you're paying for. Let's walk through a super practical example so you can really see how this hits your wallet. Say you leave a 25-watt light bulb on for 24 hours straight, right? And let's say your electricity costs 5 cents per kilowatt hour. First, we convert the 25 watts into kilowatts. That's 0.025 kilowatts. Second, multiply that by the 24 hours it was left on. That gives us 0.60 kilowatt hours of total energy transformation. Finally, multiply that 0.60 by the 5-cent cost. The grand total, leaving that bulb all day and all night, only cost you 3 cents. Pretty wild, right? Now, tracking the math for every single device in your house would be a total nightmare. So governments actually step in to help out. You've probably seen things like the Canadian EnerGuide labels stuck to the front of new appliances. These labels essentially do the math for you. They show the estimated annual energy consumption in kilowatt hours based on average use. By checking those numbers, you can easily estimate your yearly operating costs and, pick the more efficient models that will save you some serious cash over the long run. So, to bring this all together, your monthly electricity bill really just boils down to 3 major variables. 1, the sheer number of electrical devices you decide to turn on. 2, the power rating, or that maximum speed of energy transfer, for each of those devices. And 3, the total amount of time you leave them running. A 10,000-watt stove obviously uses a ton of power, but hey, if you only run it for 10 minutes to fry an egg, it might actually cost you way less than a much smaller device that you carelessly left running for the entire month. And that leaves us with a really fascinating question to chew on. Think about it. When you pay your electricity bill, are you truly paying for the work your appliances do for you, or are you just paying for the luxury of how fast they do it? Next time you sprint up a flight of stairs or push down the lever on your toaster, I really hope you remember the incredible physics happening right in front of you. Power is simply the spectacular speed of energy in motion. Thanks so much for exploring this with me today, and as always, keep questioning the amazing world around you.